And regression problems deal with continuous values, right? The scope of this lecture, that's this one by Professor Zico, he was coming from a loss to algorithm perspective. Some other people like Andre Inch came from the algorithm to the kind of loss optimization function that is used. But for Professor Zico, like I said, he comes from a loss perspective. So he was like, the loss, based on this loss, this is the algorithms that that are used here from the loss, right? Let me restart my kernel so that, yeah. So as usual, we import our libraries that we need. So more about linear classification problem. Just like in regression problems here, we also have something that's called the hypothesis function and the loss function. And the problem we are still trying to solve is similar to that of a regression problem, where we are trying to minimize the sum of the losses, right? For this particular class, they will be using the breast cancer classification, which is a very popular classification, to predict whether the cancer is malignant or benign, right? So there's a data set that I think it was gathered in 25 years ago by some researchers. And they used this. The data set was a data set of images, right? So this is something it looks like. And then from these images, they were able to gather some properties of the cancer cells, right? But I think in those days, what you would have is, what they did is they kind of found features like, let me go down, you'd see features like the area of the cell, perimeter of the cell, texture of the cell, and the rest. So they were basically looking at physical features of these cells to kind of make predictions. Well, at that time, it actually worked, but today you might not see such. What you might see is probably using a computer vision algorithm, maybe a CNN, to predict instead of explicitly looking for the different features of the cells that you're looking at. But we won't go into computer vision, of course. We'll just stick with what we have. So the data set has, the data set was taken from, the number of data points was 569, right? So meaning that they picked 569 cancerous cells and then studied their properties, yeah? And after studying the properties, they came out with 10 different features of the data, which included the area, the perimeter, the texture, number of concave points, and some other things. And then there was something they did. They increased the number of features that they had by calculating some other things that they derived some other things from this parameter they had. So from the features, not parameters rather, from the features that they had. So from the features that they had, they were able to still get information such as the mean, maximum, standard deviation, and so many other things, right? And the resulting data point was about 30, yeah, 30-dimensional vectors, right? Luckily for us, we don't need to go to the past to look for this data. Scikit-learn, which I think everybody has heard of because Teju spoke about it in the last class. So they have these data sets in their library, right? So you can actually just download the data set from scikit-learn. So for you to download the data set, right? You just do the data set.load breast cancer, and you save it into this this variable here. So I printed it out for everyone to see what it looks like. So you'd see here that we have the data, right? So this is probably it's a NumPy. It's a NumPy array, right? That contains the different. So it's look at it as a matrix where the rows are the number of data points, and the columns are the features, right? Then we have the targets, ones and zeros, where I think one represents malignant, right? And zero means benign. I'm not too sure. I think that's it, right? So you can actually, it depends on who is doing the research. You can actually switch it, yeah? But usually you would want the positive target to be 1 and then the negative 0. And then down here, you have a description of all the names of all the features, right? So we have the names of all the features, the 30 features, the mean radius, the mean texture, and so on to the worst fractal dimension, right? So for this class, the professor actually made use of just 2 features, right? 2 features for this exercise. And these 2 features were, it was actually good enough to make good prediction or separation of between the malignant and benign cancer cells. And the 2 features were the mean area and the concave point, right? So basically what I'm just talking about, we've not gotten into the linear classification. We are just more or less like talking about the whole data and everything, yeah? Data collection and everything. So for us to pick the mean area and concave points from this data, this array, in this dictionary of data, right? We will need to identify the index of the mean area and the index of the mean concave point, right? And the index will point us to the particular column that we should collect from this data, from this array, right? So doing this gives us the index of the X and index. So you might want this Y now. It's not the target value. Yeah, Y is just the second feature, which is the mean concave point, right? And then I was able to save it here so that you can see what it looks like. So these are the data we collected from the whole data set. Yeah. So we have the mean area, the mean concave point, and then the target. And then we can plot it to see what it looks like, right? So now we are separating, this plot separates remember we have our target, right? So we know the ones that are malignant and we know the ones that are benign, right? So now we separated the malignant and benign data with colors, yeah, and also the plus and X. And you'd find out that 1 represents benign, and like I said before, 1 represents benign, which is the blue data points that we have here. And plus 0 rather represents the malignant cancerous cell. So what can we say about this particular plot that we have here? Is it similar to what we have in a regression? Do you think we can use a regression algorithm, maybe linear regression, to solve, or probably, let me just, okay, what do you think our goal is given this kind of plot? If you want to speak, just raise up your hand and I'll ask you to unmute. Okay. There's no hand up. Okay, Ademola. Okay,
hello, can you hear me?
Yeah.
Yeah, so we want to predict based on 2 possible outcomes. That is, giving a certain input. We want to know whether it is either malignant or benign.
Okay.
So yeah, so drawing, we want to use the line of best fit. We can only based on a certain threshold. We're going to use a certain threshold to determine whether it's either malignant or benign. So that's what I think.
Okay. I know I think you're picking idea from, yeah, it's right. So thanks, Ademola. Okay, there's another Ademola that wants to speak. Okay. The other Ademola.
Okay. For this particular problem, you were asking if we could use linear regression for it.
Yeah.
And yes, my answer would be no. And the reason we did that, if you look at the graph that we just have now, there's a bit of the blue, the benign data. You can see that it's clearly different from the ones that we have in red. So there's no way you can draw a line of test and diagonally like we did with the linear regression. So what we will do here would probably be that we would have to separate. There will be a line that will separate.
I think we lost you, Ademola.
Most likely.
You said,
hello, can you hear me?
Okay, it's better now. You said what you'll say is a line that will separate. Yeah.
Yes, a line that will separate the blue from the red. There will be like a threshold, so that I would know that once it's above this particular threshold, it's likely to be malignant, and if it's below, we can classify it as benign.
Okay. That's nice. Thanks. Yeah. So both of you are correct. Yeah. So, but let's look at it in more details. Okay. So, like they said, for classification problem, remember we are dealing with discrete values. So meaning that it's either, if it's going to be binary, it's either a 1 or a 0, just like we have in this case, right? It's not it's not continuous, where you'd have something like I know in the last class we did something like predicting peak loads. Yeah, that was peak load. So peak load won't be, you can't have a peak load of 1 or 0. It doesn't make any sense. So, but if it's a continuous problem, you just want to find the line of best fits that passes through the data, right? But for this one now, you are going to be like finding a line that's approximately separates, I won't yet say perfectly here, but kind of separates the greater portion of red values to the left, to the right, and then the blue ones to the left. Yeah. And another thing you'll notice from the data is that even visually, you'll notice that a cancer cell is, these are some other things you can notice. A cancer cell is usually malignant if the area, if you're having high values of mean area, probably greater than 1,000, and the mean concave point is usually, if the concave point is greater than, say, 0.1. So most times you find that based on this data we have here, you find that it's more likely to be malignant. It's more likely to be malignant here, right? And based on that simple intuition, this plot was derived. So this plot is not, it's not from any machine learning algorithm or model or anything. So this is just based on intuition, right? Just looking for a line that kind of separates the red values and the blue values. But someone might say, oh, this looks fairly okay, right? But you can't actually say this is really optimized, because by the time you pass it through a because why you wouldn't say it is really optimized is because you don't have a good sense. You can't from your brain just think of the loss that you would have based on this random plots that you did. And because you don't have that intuition, this is not, you can't really say this is really optimized. So that leads us to defining the loss that would correctly classify the malignant and benign data that we have. So for the classification notations that we are going to be using is very, very similar or same to the ones that we used for regression, right? So we have the normal input features, right, X, and the number of data points from 1 to m, right? Then we have our output Y, which is binary. We have our parameters, right? We have our hypothesis function, our loss function L, and the optimization problem that we want to do. And the optimization problem is basically we are trying to minimize the loss from the hypothesis, between the hypothesis and the target value for all the data points, right? That's our optimization problem, both in regression and same thing in classification problems. And okay, so there's something that is worth noting here. If you have gone through some maybe lectures on, it depends on the one you go through here, you'd find out that usually what you would have is, let me see where it's written here. What you would have is probably 1 for maybe a classification between 1 and 0. Maybe 1 is the one that is positive, 0 for the one that is negative. But for this class, the professor used a different convention where he used -1 and 0, right? And this is what he used throughout the course. So it's best we just follow what his own convention of this stuff. Now, before I go on, there's something I want to check for 0 loss. Okay. Okay. Sorry. Okay, so I'll just read what he wrote here. So now remember I said that he's going to be using a -1 and 1 range, right? And basically what it's trying to say is that, okay, let me start from here. The other notable difference is that prediction space, yeah, is actually still the same as was in the regression settings, Y of R. This may seem somewhat counterintuitive. We have outputs in the discrete space, -1 and +1. So unlike in some other examples that you would have 0 and 1, here we are having -1 and 1, and the predictions are real valued. Intuitively, the output of our hypothesis function will correspond to some notation of confidence, right, in our prediction. If the sign, now listen to this carefully, if the sign of H of X, the sign of H of X determines the most likely output. If, okay, we are predicting positive if the sign of H is equal to 1, and negative if the sign of H is equal to -1, right? But the magnitude indicates, however, how certain we are. Large positive values of H of X indicates we are very confident that in our positive prediction. Very large negative values indicates that we are very confident in our negative value. So basically it's trying to say that if you're having large positive values of H of X, it means that you are tending towards the positive region, which is of +1. And if you're having very large negative values, you are tending towards the -1 region, right? And the value is around 0, right, for the loss. Without these notations of confidence, it's extremely difficult to formulate a smooth loss that can be optimized with gradient descent for example. I think I'm still going to explain this better in somewhere down. I think somewhere around here. It's not so long. I think somewhere around here. Yeah. So let me just leave it for now. I'll explain it better down here when we are talking of 0, 1 loss. Okay?
If I can just say something.
Okay.
So this is the normal notation when you're dealing with most machine learning text. They do -1 and +1 exactly because of what Professor Zico said, which is that if you start dealing with other algorithms, say supervector machine, you want to start looking at the sign of the prediction itself, not the value. So you want to say sign of this. When it's negative, then we have the negative class. When it's positive, then we have the positive class. And it comes handy in a lot of other scenarios where you look at the sign itself and use it to kind of like look at how the gradient is flowing. Is it in the positive direction or the negative direction? So like Kenichi said, it's notation, but a lot of, if it depends on the school of thoughts of machine learning, like where you're coming from, then that sort of like drives your notation. You can go ahead with this whole problem without trying to formulate the output as negative, between -1 and +1, you know, but yeah, that's one of the confusing part of this field. It's like different people lean towards different sort of
Different things. Yeah. Okay. So I think we'll still talk about it later. So now the instantiation of the cancer domain, right? So remember we have two features, the mean area and the concave point. And now we are adding a 1. So who can tell me why we are adding the 1, right? Remember it's a linear classification. I think it's those who went through the last class that will be able to answer this. Okay, nobody. So the reason why we're adding the 1 is for the intercept function. So remember the very simple model that I wrote then in the first class, the first machine learning class, where I said y equals mx plus c. And then we're like, m is your θ1 and c is your θ2, right? Now, if you're going to be doing matrix multiplication, yeah, between your x and your θ, it means that you should have two values of θ, a m by 2 matrix for your x, and something similar for your θ, right? So, but that other value of x is 1, right? The coefficient of θ2 is 1, right? So same thing here, the coefficient or the intercept function that you would have in your equation would have a coefficient of 1, right? So that's why we have 1 here. Okay. And we have our outputs here, which is -1 and +1. So unlike what we had here, 1s and 0s, we would have to change these 1s and 0s to -1 and 1, right? And then we have our parameters that we all know, and then the hypothesis function, which is your θ transpose of x, right? Okay. So now let's talk a bit about the loss function. So this is very similar to what, this is more or less like an explanation of what the question I asked here, that how would the regression problem work in this particular plot here, right? So in this particular problem. So let's assume this is, say, it's supposed to be a classification problem, and we are using the least square methods to kind of optimize this. You would find out that if you use least square, which is usually used in regression problems, that's the least square method of calculating loss. You'll find out that you have a plot of this, a plot like this, right? It's trying to find the line of best fit between your data. But in the real sense of it, this is actually what you want, So you can see that there's a wide difference between what your regression problem is trying to solve, which is actually correct if you look at it in its own. So now it depends on what you are trying to do here, but so far you're doing classification. This is actually going to give you very wrong predictions, because if you look at this plot very well, right? This least square plot, which is red, is trying to say that everything here, let's say everything here belongs to the +1 class. Everything down here belongs to the -1 class. But in the now it's more or less like an up-down classification, everything up and everything down. But in the real sense of it, it's not an up-down classification. It's more or less like a left-right classification, right? So it means you are going to be accounting for very, very large losses if you are using a least square approach to solve this problem, right? Is it clear? Is it clear? Mteju, your hands is up. You want to speak? Okay. So now we'll be looking at now we haven't spoken about any specific loss function, yeah, that is used for classification, but a very intuitive one that you can look at when you're thinking of classification problem is the 0-1 loss. So the idea of the 0-1 loss is, like Teju said when she was speaking, is you are kind of using the sign values to know whether whether you're having a 0 loss or a loss of 1. So the idea is that if you're having 0 loss, a loss of 0, it means it's correct. And if you're having a loss of 1, it means it's not correct, right? So now, here it's saying that, okay, just leave this. Just look at this now. It's saying that, okay, let me go back up here. So if the sign value, if the sign of h of x is equals to y, then it's 0. So it's what it's saying that now, this is not sign as in, where do I write now? It's not sign as in, let me put something down here. It's not sign of HO, not this sign. So it's just saying the sign value. So let's say your H is equal to minus 2.3, yeah? So it's saying if this sign minus 2.3 is equal to the sign of y, it means that your loss is 0, right? Meaning that it's in the positive region, right? But if your sign is otherwise, that means your sign, even if your sign is a plus and your y is a minus, if they are both different, you are having an error. So the idea is that, remember, we're having a 1 and -1 loss. So you're trying to say that if your prediction is having a sign that is equal to what you have in y, right? That means it's correct, no matter what the value is. But if the sign is something different, it is not correct. Is it clear?
Is that a mistake? You wrote SIN. Is that what you wanted to write?
No. So I said it is not this SIN. It's not sign H. That's what I said, not a mistake. So I told them it is not sign H. It is actually the sign of H.
Okay.
Right? So don't look at sign of this as probably a mathematical expression. No.
Yeah, I also found it. It can be confusing, and if you never find it confusing, you are not alone. I used to think it was meant to be something bigger, not just a sign. It's just plus or minus. That's all it means. So an example would be if you have an array. Just think of it as having an array, and all you have is positive, 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 negative, negative. And if you could just write that down, Kenichi, just like have just a y, your normal prediction. Imagine your normal prediction equals to positive, positive, negative, negative. You only have two. You only have 4 data points, which is positive, positive, negative, negative.
Yeah. How do you want me to write it?
So like a string, positive, positive.
Okay.
No, like plus, like what you
Oh, okay.
go plus, exactly. Yes, like 2 positive, 2 negative.
Man, I've forgotten I'm using marker.
Yeah.
Okay.
And then you have your prediction as 1 positive, 3 negative. So the question would be, what's your loss?
You said your
Like maybe your y hat is like 1 positive, 3 negative.
okay.
So in this sense, if you wanted to calculate your loss, what would that be? So
are you talking to me or to the class?
I'm talking to the class actually.
Okay.
So from the definition we have there, we have your loss is 0 if the sign of your hypothesis exactly equals to the sign of your label. So if you look at it, you have 4 data points. Is y1 the sign of your first hypothesis? Is it equals to the sign of your label? True. So what is your loss?
0.
Exactly. How about the second one? What is your loss?
1.
Exactly. The third one, what is your loss?
0.
And the fourth one?
0.
Yeah, that's it. That's all what the mathematics is saying. Nothing apart from that.
You just made it so easy for me. Thank you very much. So this is what I've been trying to explain in this whole grammar here. So this is exactly what Teju just described here. So if you were following, or if you were not following, I don't know again. So what this is trying to say is that wherever the sign of H is equal to Y, wherever this is equal to this, your loss is 0. Else your loss is 1, right? And a simple way of representing this whole notation here is this, where you're saying that if the value, so now this is more or less like the simple compact way of writing it. So now if the product of H and Y, right? Of course, you know what product is. Minus times minus is what? Plus, yeah? Minus times plus is minus. Plus times minus is minus. So it's saying if the product of H and Y is less than 1, it's less than 0, then it's a wrong prediction, 1. Else, it is a correct prediction, 0. So it's the same thing here. It's just that now they brought it to multiplication. You're now multiplying these values. A minus times a minus is a positive, is a plus, yeah? A plus times a minus is a minus. A minus times a minus is a plus. A minus times a plus. A minus times a minus again is a plus, right? And, well, like Teju said, different people do different notation. You can even decide to change your notation and say, if your value is greater than 0, right? If whatever you have here is greater than, does that make any sense? Yeah. If your value here is greater than 0, then it is a 0 here. Else it is a 1. So you can just play around things, but we are going to be following the convention that the professor used.
Yeah, so it's important that we get ourselves familiar with this notation, because especially if you're considering grad school, you will find it. And it's sort of like when you start intuitively trying to understand what they're saying, you realize that it is so simple. It's not as difficult as the notation looks like. And just like Kenichi has said, you have an indicator. So what you have when we have 0 is when this is equals to this, it is 0, 1 otherwise. It means we have an indicator, right? 1 or 0. So if you needed to write this in a compact way, you can think about it. It's it's almost very, very intuitive that if you do that, the normal mathematics product thing, you would get positive, negative times positive is negative. Then that if you're in the negative region, you are what? You're less than or equals to 0. So 0 is, you can, like 0 is like 0, right? It's neutral. So if you're in the negative region, you're either in the negative region or you're in the positive region, or you're exactly equals to 0. And that is what this is saying. This is saying that if your data set is less than, or equals to 0, then you have a loss of 1. Not your data set, sorry, your hypothesis that times your target. So it's just to make it, how do you mathematically represent it? I mean, instead of you writing if h of x equals to y, this is 0. Otherwise, this is, if you want to write if this else this, instead of doing that, you can just write it in one line. And that's all. It's just mathematical convenience if you want to think about it in that way.
Mm-hmm. So guys, don't think too big about this thing. They are very, very, very simple. Trust me. If you take it step by step. Okay, so let's go on. So so now let's plot what this loss function that we just described here, what it looks like. So now let's say we have 1,000 values ranging from -3 to 3. Yeah. Now this is the same exact thing that we just said here, right? So this is going to give us a bunch of truths and false. Yeah. So where it is less than or equal to 0, it will be a true. Anything other than that would be a false. And you find out that our plot is this. So for every value of h times y that is less than, so now it's not like we are taking a real hypothesis and a real target value and multiplying it. We just say, let's assume that our h times y is within the range of -3 to 3, right? If we plot that here, you find out that all the negative outcomes are towards the right and towards the left of the x-axis, and you find out that the loss is 1, right? And all the positive outcomes is towards the right of the x-axis, and their values are 0. Yeah. And I don't know if it is correct to say this is like a step function. It looks like a step function, right? It looks like a step function, but this is not. Yeah.
No. Yeah, you can. Usually they call it a step function. It's like, yeah.
Okay. So okay, that's aside. But you see, the thing is that this whole loss that we just described has its flaws. You can't really optimize this loss for some mathematical reasons, which I'm not sure I've really explored. But one of the reasons that was stated here by the professor is that, look, the first reason is that it's difficult to optimize, right? Of course, it's too simple, clearly difficult to optimize.
No, it's not, because it's too simple.
No. So if it's for you to optimize it, you will probably have to find the partial difference, find the gradient of the loss function, which I'm still wondering. In my own honest self, I'm wondering how you would find it.
Exactly. So we need to go back to looking at the diagram. So in real life, this is the optimal loss you want. This is like 0-1 loss is what is it's the optimal loss. It's the loss that we want. But we cannot optimize this. We cannot learn with this loss. If you look at it, there's nothing, when we're talking about optimization, we're talking about, is there a way that we can look at a loss function and then we can move down in a gradient kind of way? So imagine, remember the linear regression function that you had a straight line. Then you know that if you find the gradients, there is a gradient. But if you look at this loss,
there's no gradient.
There's no gradient. The gradient is 0. Like you can't
zero.
Gradient. You cannot learn with this loss. So it becomes a challenge, which is like an extremely big challenge. If we could learn with this loss, this would be the perfect loss that we want. But it's impossible. Like you cannot optimize. It's difficult to optimize. So that's sort of like the setback of the 0-1 loss. It's not optimizable.
Then it still throws more light to what he said here. So it says that the derivative is equal to 0 everywhere. Yeah, except
like,
0.
Exactly.
Because you're having just straight lines in the
exactly.
x-axis region.
At 0, the derivative at 0 is undefined. You cannot define it. That's one of the problems with ReLU, if you recall. I'm sorry, some of you might not know what ReLU is. So if you just look at the graph, you can see that at 0, ReLU is undefined. But if you look at the other curve, it's either 0, undefined at 0, then in the positive region it is 1. So if you think if you think about it as that. So yeah, that's sort of like the problem with the 0-1 loss.
Okay. So let's move on. So this will lead us to other kind of losses, or better kind of losses. Like I told you,
we don't want to say better. We want to say that it's an approximation. Like this is the best loss that you need, but you cannot
intuitively, but you can't use it.
You can't use it, so you need to find an approximation. So we we cannot exactly say they are like better, but we can say they are good approximation
that you can optimize.
Yeah, and they are optimizable. You can actually learn something useful with them using like technique. The only tool that we have as machine learning engineer or science, like researchers, our toolbox, we don't have too many. We only have like gradient descents. So we need to be able to gradient descent on something.
Almighty gradient descent.
Yeah, we need to be able to gradient descent on something. So, and we cannot on this loss. So we have to move forward.
Okay. So the three loss that he spoke about is the logistic loss, hinge loss, and the exponential loss. Yeah. And this is what they look like. So for the logistic loss, he's saying that for large, not he's saying that, the equation is saying that.
I was going to speak. Just like, what do you mean saying that?
It's the equation that is saying it, yeah, because I had to look at the equation. I didn't listen to him. So for large positive values of this, yeah, that's large positive. This is basically the behavior of exponential functions, yeah. So if you're having large positive values of h times y, the exponential of that, the exponential of the negative of that output is going to be very close to 0. So the loss will approach 0. But for large negative values, yeah. What am I saying? Sorry. Do I need my glasses? For large positive values, will be very close to 0. So the loss will approach 0. Okay. For large negative values, the log of this is approximately equal to this. So the loss increases linearly. Okay. Okay. Okay, so what he's trying to say here is that if you're going to be having large positive values of this exponential function, if you're having large positive values of h of y here, and then you find the exponent of this will be close to 0, meaning that whatever you're going to be having here is going to be a log of 1 plus something close to 0. Tejo, please, I don't know if who has a calculator there to check what log of something close to 0 is.
So the thing is that it's just using definition of what, like the graph of logarithm. So I understand this might not be intuitive. So you just need to instead even if you're not trying to use the calculator, log of 0. If you like the log of 0 is what is that should be. Sorry, log of 1 is 0. Yes, log of 1 is 0. And as you move down to the negative side, it's undefined. So that's like that's the graph of logarithm. And if you can just like Google it, just graph of log to see what it means. And the exponential, it's like they are in the family of they are very close. So if you look at the graph of exponent as well, so as you are moving forward, like exponent of 0 is what? Is 1, right? At 1, exponent of 1 is 0 rather. Is that correct? I'm saying this.
No, exponent of 1 is not, I don't think so.
Exponent of 1 should be 0. Yeah, I think so.
Sure.
So let me, that is something. I mean e to the 1. I'm sorry, that's bullshit. E to the 0 is 1, and e to the 1 itself is 2.718. Anyway, that's beside it. So for this logistic loss, it's saying that for large positive value of h of x times y will be very close to 0. Can you just go to Google and check
So I think
exponent, so it's easier to see as you're going further ahead, like as you're increasing the value on
now
x.
this is our logistic. This is the logistic. Hello.
Yes?
Hello. Okay, so I was saying that the plot is here, but what it's trying to say is that this is the logistic function here, right? So it's saying that when we have large positive values of h times y, right? And we find the exponent, you'll find out that this whole thing here will be tending to 0 because the log of 1 is actually 0. Yeah. So if you're going to be having log of 1 plus something that is close to 0 here, right? Remember we said that this is going to be very tending close to 0. So meaning that if it is tending close to 0, this whole value here is tending closer to 1. So the log of 1 is going to be tending towards 0. The log of 1 plus whatever is close to 0 here will be tending towards 0. But in the other hand, what we are going to be having, if we are having large negative values here, we are going to be having something closer to this value of minus h of x times y. So it's more or less like the values of minus h of x times y trying to move down to the value of 0. I don't know if you guys understand what I'm trying to say. So if you check the plots here, right, you'd see that the logistic loss, which is the orange one here, you'd find out that this anything closer to the left, it's something closer to the negative value, and then as it comes down, the values are tending towards 0, meaning that you are having high positive values of h times y. Does it make sense?
I mean, it's not important for you to exactly understand everything that is going on mathematically right now. With time, you can always go back to the text and try to make sense of it. But
okay,
basic intuition lies, and it's just trying to explain what it is. And if you find it difficult to understand right now, it's totally fine. It doesn't mean that you should be disinterested. Just
no. So the general form, don't be disinterested. The general idea is that we are trying to reduce the loss. Do you understand? We are trying, just like we have the hinge loss here, trying to come down to 0. The logistic loss is the objective function now will be to reduce the loss such that it tends towards 0, right? Are we clear? Are we clear? Okay, I assume we are clear. So the hinge loss is a bit different. We are saying that if we are having we are picking basically the maximum of a 1 minus the hy. So permit me to be calling the h of theta times y hy. So the value we get from 1 minus hy and 0, whatever the maximum is, that is what our loss is. So what you'll find out that so far, like he has said, so far what the hy we are having is greater than 1. The loss will always be 0. So what we are saying is that we should actually be looking for what our objective should be to what our objective should be should be to kind of find high values of h times y, right? so that we have lower loss. And then the exponential function is this. We are finding the exponent. And then for similar reasons with the logistic loss, the loss will go to 0 for large values of this, but negative for values of, but for negative values of this, it increases very quickly, right?
And you can
So
almost imagine why it would be.
Okay.
Right? If you look at from looking at the curve, if you have exponential negative, I negative, what does that give you? It's very close to 0, right?
Mm-hmm.
And if you have exponents of I positive, where does that lead you? It's almost like it's undefined. Like it's like you go very, very positive, then it's very, very, very large, then it's undefined.
Which kind of tells us that exponential functions are very, very sensitive.
I mean, log also gets to undefined from in the negative, like in the negative region, not in the negative region. So if you have log of 0, then log of 1, then you're like going down. Like I'm trying to imagine the curve. So log of 1 is 0. Then anything outside it is like log of 0 is undefined. So they all have their own their attributes. It's just like, I mean, something that helped me with most of this function is that I know what they look like. So when I'm trying to talk about them, it's not like I'm trying to memorize what this formula is saying or something. Intuitively, I'm trying to look at what the curve looks like visualize what the curve looks like and try to see what the behavior I'm expecting when I start putting the values of X in it. So if you're talking about tan or sine or something at your leisure, you can just like look at the curve and try to understand what the curve is saying, because that would help you better intuit a lot of some of the things you see. But there's no rush. You have a lot of time to do that.
Yeah, is just know that you have to kill yourself if you're not getting it now. Okay, so this is what our loss look like. Right. And then in solving the classification, okay, can you hear me? Okay, I think you can hear me. And in solving the classification task, as this, so this will loss, right? Yeah. So he kind of brought it down to trying to understand the loss and how the loss affects the training process and the whole optimization. For some people who will go through Andrew Ng's course, Andrew Ng's kind of approached support vector machines in using a geometric perspective, yeah? So, but we are not going to go into that. We'll just stick to what we have and make sense out of it, right? So, but for support vector machines, yeah, you have the linear SVMs and the kernel SVMs. Basically, what it's saying is that you would want to use a linear SVM when you have a linear kind of data, right? That's when I mean linear, it's basically saying you want to use a line to kind of classify the data points, right? But when it goes beyond just a kind of 2D data, then you'll be talking of something that is non-linear. And for non-linear kind of problems, you'll be using a kernel SVM. And this is how it's defined, like the hypothesis function, this is how it's defined. So for the linear SVM, it's very, very similar to what we have in linear regression that we did last week, yeah? So you're having H is equal to the theta transpose times x, yeah. But for the kind of SVMs, you are having theta k of x and x prime, where k is the kernel. Well, you would notice something here. In the linear SVM, our j is the same, let me say is in the same dimension as your x, which is your input features, right? So we are still, remember, it's linear classification we are dealing with, but since he gave a little intro to what the kernel SVMs do, that's why I'm talking about it a bit. So one similar subtle change, not subtle, but it's a kind of a major change, and an interesting one for that matter, that you find in kernel SVMs is that your theta, it's not actually in the same dimension of, it's not the same, or let me say, it's not the same number of theta that the theta is not the same as the number of features you have as you would have in this particular one here. So notice, this is where you see mathematical notations. Here you're having theta of j, where j is the number of features that you have, right? And remember how we said I is the number of training examples that you have. But here, our theta is of I. So meaning that we are having theta for each of the training examples, not for each of the features that we have, right? So that's one kind of interesting thing that you will notice in SVMs, in kernel SVMs. And remember, like I said, it's for non-linear problems, right? Okay. And then, like we said before, it uses a hinge loss, right? And this is the hinge loss, just like we have defined here. So remember we said hinge loss is what? Hinge loss is this, h of x times y, yeah? 1 minus h of x times y, comma 0. So it's the same thing we're having here, 1 minus, this is your h, right? That's theta transpose x, because, of course, that is what we have here, right? Times y, then comma 0. So we are maximizing this. Well, you will notice that we are having something extra here. So this is called regularization. Basically, it's for regularization, where we bring in a regularization parameter. So the idea of regularization is, I know he went into more details. Let me check if he said he went into more details. Yeah, he went into more details in regularization. And even if he does, I'll personally do go into more details and visualization of the effect of regularization in training. But basically, look at it as you're trying to make your training not to overfit. Yeah. So it goes in two ways. It's more or less like a trade-off between your bias and your variance. You don't want your model to be biased towards the data that you have. Neither do you want it to be short-sighted to the things it should predict, right? So in trying to overfit, right, your regularization parameter kind of tries to make it a bit, reduce that complexity that is trying to attain. I don't know if you understand what I'm trying to say. So look at it that it's trying to make this particular parameter here is trying to make your training process to be such that it does not get too used to the data, such that if you bring external data, it will kind of misbehave or misclassify. I don't know if you get what I'm trying to say.
Again, I would just like to add, it's okay if you don't understand everything that is going on right now. I can assure you it's very, very, very mathematical, involved, but assimilate or take in as much as you can. And it's okay. You can always come back to it at any time. So don't feel like this is too much. I can't do it anymore.
Maybe can I give an example? Okay.
Yes, if that would help, please go ahead and do that.
Okay,
and it helps to skip some of these mathematical details, and we can always go and come back to them later. So
okay.
you can always skip some of them if it doesn't seem like.
Okay, so let me try and explain. Let me use maybe a real life example, right? Let's say I have a child, right? And I'm teaching this child, I'm trying to teach this child to know houses when you see houses, yeah? Now, the kind of house I've been showing this child is a bungalow, right? No, a bungalow, is this the right example? Okay, basically bungalows that are red and duplex that are blue, right? So now, each time I take this child out, I tell him, what is this? He makes mistakes, yeah? And I correct him. What house is this? Let's say it's a blue house, a blue duplex, right? And he says it's a red bungalow. I correct him and say this is a blue duplex, yeah? And we do this to the extent that the child is very, very accurate when he sees blue duplex and red bungalow. Now, you can look at it as the child has crammed blue duplexes and red bungalows. So when he sees anything that is blue and up tall, it is a duplex. And he sees something that is red and short, it is a bungalow. And now I bring something else to this child. I bring a red duplex and a blue bungalow, and I say, what is this? And the child fails. It invariably means that the child kind of crammed what he saw. You understand? You wouldn't want that. Basically, what you would actually want to do is probably bring different examples so that the child learns from. But another way of kind of trying to reduce the complexity or trying to reduce that cramming process of the child in our own situation here. Let's say this whole training process, we are trying to train a child here, is to bring in a regularization parameter. So it's trying to regularize the way it is learning so that it does not cram. Does it make any sense? I don't know if it made sense. Or is there any question with what I said? If you have a question, raise up your hand. Okay, stop already. Okay, since there's no question, I guess everybody understands. So I can just move on. Okay, yes, it does. Makes sense. Okay. I was just checking the chat now. Okay, so we are cool. Right? And this is what we'll have for the hinge loss. Yeah, it's the same thing with what we have here, right? Hinge loss. So you find out that it kind of reduces linearly, and then once the loss is 0, it just puts 0, right? So this kind of makes sense based on the loss function that we have defined here, right? So it's like any value that we get here, else 0. So any value that we have here, else 0, right? And remember, the idea is that we want to be able to find the gradient, and the gradient should be such that we can optimize it. Yeah. No, we want to optimize it. The idea that we want to find the gradient, and then kind of just like in linear regression where we want to be able to update our weights based on the gradients that we have calculated, right? And I won't go into much. I won't even go into the mathematics. But what we are going to be finding out here is that we are finding the partial differential of the loss function that we have defined and the regularization parameter. And what we have at the end of the whole mathematics here is this. So this is what we have here. So that you can kind of rewrite it in this format here. So the reason why we are rewriting it in this format is because we are you want to look at it as matrices, right? So that's why we're having the capital letter X transpose of Y, right? And 1 and all this. And if you take this, just the same way we did training in the previous lecture, it's the same thing we are going to do here. So we are saying, we are looking at this. Remember, this is our loss function. We are looking at this particular function, and we are writing what this function is. So just look at it as the same thing we had in the previous class. We are bringing it to this class, but we are just changing the partial differential of the loss function. So we are going to be having this particular equation here, right? So if we iteratively update our alpha based on this gradient that we are calculating here, you would find that we'll get an optimal theta after some number of iterations. Does it make sense? So now we are having loss and error here. We are just basically saving the loss to kind of plot it and see what it looks like, right? To have a sense of how the loss reduced through the training process. Are we clear? I guess we are clear. Okay. So this looks like a whole lot, but the truth is it's actually very, very straightforward. Just take it line by line and you see it kind of makes sense. It makes sense, not it kind of makes sense, right? Okay. And then we'll have to define our function that will normalize and unnormalize our data, right? And the way we are saying we want to normalize is that we are saying the values of x minus the minimum value of x all over the maximum value of x minus the minimum value of x, right? Okay. So, okay. So remember something. Remember something. This is our x value. So what you notice in this line of code is that, yeah, it looks a bit big and all that. We are just picking the first data point here. That is, what is our first data point? That was mean what? I can't really remember the name. Mean area, yeah? And then this is mean concave something, yeah? So this is it here. And then we are adding a vector of ones to it. So remember I told you we are adding ones because of the intercepts, the intercepts that we have in our data. So one is just basically the coefficient of that intercept. And then we are transposing it so that we'll be able to do matrix multiplication with our theta, yeah? And then another thing we'll notice here is that the values of y in the data that we have are all ones and zeros. And we already agreed that we are going to use -1 and 1 for this part in this for this whole intuition, basically, right? So we convert our y's into -1s and 1s, yeah? So what you would see, okay, let me run this. So this trains the data. So that's why it took took a little time. Yeah. So we did a copy, put it in new variables, yeah? And then we define our ranges. So you see true, true, false. So what true, true, false means is that we are normalizing the first column, which is our mean area. We are normalizing the second column, which is our mean concave something. And then we are not normalizing the third one, which makes sense. There is no reason for you to normalize one. All right? Why should you be normalizing one? It's just your coefficient. If you normalize one, it's actually going to change your result. And you shouldn't actually. Yeah.
The question would be, even if you normalize one, what will you get? It's already normalized.
It's already
One
normalized.
is normalized.
It's normalized already. Okay. So, and then we pass our values into this function that we have defined, yeah? X, Y, alpha, and the eta, and then lambda. So who can tell me what lambda is from this function that we have written here? Please, what is lambda? Let me use this small time to rest, 2 minutes to rest. Who can tell me what lambda is? You can put it on the chat. That's this lam. So if you don't know what lam is, you can look at this. You can look at this equation here. You can look at this one here too, and then try to figure out what it is. No response. I'm waiting. You don't need to write long notes. Just write the name of lambda, the right name of lambda. Ah, no response. God of mercy. Okay, Obiora just said it. Yeah, so I'll move on. Okay, so it's the regularization parameter. Yeah, that's lambda. Okay. So you notice this is lambda here, and we are using lambda here, right? So if you look at this equation here, remember I said this equation is the same as this equation. You'll find out that lambda is here also. So this 2 lambda theta, 2 lambda theta. So it's very, very straightforward, right? It's the same equation that we have here that we are writing here, right? So we pass in the different parameters we want into this equation, and we are returning theta, the loss, and the error, right? So this is what we have here, right? And this is what our theta gives us. So we are having 3 values of theta because we are having theta 1, theta 2, okay, or theta 0, theta 1, theta 2, which have coefficients of x1, the mean area, x2, the mean concave something, and x3, which is 1, right? And then we can plot this. So he used a contour plot, which is quite interesting because he's trying. So the reason he used contour plot is because he's trying to account for more than one something that is in more than 2 dimensions. Yeah, that's when you usually find contour plots. But for now, we are just looking at the results. Yeah, so you find out that this particular SVM that we have defined here, based on the optimization function and all the things we've defined, you find out that this is the line it uses to separate the malignant and the benign cancerous cells. Yeah. So if you compare this with this, no, is it this? Yeah, with this, you find out that there's a large difference. Yeah, there's a large difference, and then by the time you even check the loss, you find out that yeah, this actually when you take account of the loss that you have, find out that this kind of makes more sense based on the loss. You are not mind you, you are not defining how good a model is based on what we are seeing or the plots you are plotting, yeah. But you know how well the model is, right, or how well the model has trained based on the loss values that you're able to get, right? And that's part of the reasons why we saved the values of the loss. Yeah. And then he went over to see what happens at different iterations. So you find out that at different iteration values, you find out that it's gradually trying to fit itself to become this that you're seeing here. So at the first 10 iterations, yeah, you'd see that it's still something far away from what you would define as correct, even by looking at it. Then after the first 50 iterations, it came a bit closer. Some people might stop here and say it is good, right? From your own human understanding, but that would be actually wrong, because if you kind of track the losses that you're getting, you find out that it's not really a good loss. The loss, we will find out that the loss still has potentials to reduce. Yeah. Then after 100 iterations, we find out that it's something very, very close to what we have here. Yeah. Okay. And then let's say we plot the loss. So this is what the loss looks like. Usually, when you're using hinge loss, I think the first iteration gives a very funny behavior. That's why you find out that it started with 1 and then came down and then gradually reduces, right? So now as it's going up, yeah, increasing, it's actually reducing the loss. So it started with a very high loss at this point and gradually reduces until this point. So at this point here, I can actually say that it has, it still has potentials of reducing if you keep on iterating, right? So let's even see what happens after 1,000 iterations. This 1,000. Okay, no, yeah. So now say after 1,000 iterations, it begins to flatten, yeah? Meaning that there's no, the changes are actually very, very, very minute, right? And then we can also plot the error. So the error plot is just telling us, giving us an idea of how the errors were reducing, right? So you know, over here, where is it? Where is it? So you know, over here, to get the loss, we are kind of getting a bunch of true and false, right? So we are saying that for all the values that are less than 0, meaning that it's a loss, yeah, we want to find the mean. And you find out that if you're finding the mean, initially, if you're having very large numbers, right, your mean would actually be very high, right? So you find out that gradually, it kind of increases. The loss kind of increases until it flattens at this point here, right? Okay. Yeah. Okay, so you see it flattens. The loss isn't changing here. It's not actually changing here. Okay, so that's that for the support vector machines, right? Now let's now look a bit more into the effect of normalization, right? Talking before. So there are actually different ways of normalizing. Yeah, there are different ways of normalizing. The one we used before is one way of normalizing, where you have your input value, right, your feature value, minus the minimum value of x, yeah, for all the different columns, all over, for all the different columns of features, yeah, for all over the maximum value of x minus the minimum value of x. That's what we had in the first, that's what we used for this particular training process, yeah. But you can have other normalization methods. In this case, you are saying the feature values, right, minus the minimum value of x, over the maximum value of x minus minimum value of x minus 1, right? And then you are multiplying all this. Okay, but you are still multiplying the numerator by 2. So you're saying 2 times this, right, all over this minus 1. So this is another way of normalizing, right? And it has its corresponding way of unnormalizing, right? And then there's another method which is more generally used. In fact, that's the one I'm kind of used to, right? Is where you're saying your x values minus the mean all over the standard deviation. It's as simple as that. So you're saying the x values for the different features minus the mean value of all the different features, feature columns, yeah, all over the standard deviation of all the data points in the feature column, right? And here, over here, we can see the behavior. Okay, you can see the behavior, right? So the behavior of this particular normalization, yeah, you would notice that it's not, it's kind of different from this one. It's kind of different from this one. The starting point of this one is kind of sharp, yeah, it just starts from 1 and then before it gets itself and then starts reducing gradually. But over here, you find that it didn't really have that jump start, yeah, but it still does the job, yeah. And this is the loss. This is the loss here. But unlike these two that we have seen, the second one, which I said is more generally used, yeah, you'll find out that it will give you something like this. So you see that this one is kind of a smoother way of, it kind of gives a smoother plot of your loss and of your error. right? And this doesn't just only affect the way the loss is or the loss plots. It actually still has effect on, it actually still affects the outcome or of your model, right? So I don't know, but look at this one closely, right? And then look at this one here. You find out that there are differences. So now let's take this point, this plus here, for instance. Here, you find out that the line kind of goes a bit up. Yeah, you'd see a space here. But here, it's kind of closer to this point here. Right. So it shows you that your normalization, the normalization you choose to use for your training has effect on the outcome that you're going to have. Right. Okay. I think I need, I think 2 minutes to catch my breath. So about that 2 minutes, I'll use it to answer questions, if you have questions. Okay. Someone wanted to say something. Okay, Judy.
Yes, thank you. So how do we now know which of the normalization techniques that we're going to use?
So what I would say is, already you would see that the last one is actually, for this particular problem, is actually the best. But it still depends on the kind of data that you have and what you're trying to achieve. I would always say that. So for researchers who are doing research on machine learning research, they try out a lot of normalization and see how it affects their training process here. But for me, most of the time I've used this last one, which is the data minus the mean over the standard deviation. Okay. Is there any other question? Okay. I think I need to get water, please. Teju.
Did you mention my name?
Yes. I was like, please, can you help me? I need to get water. Like my throat. Just
Okay.
so you can just ask questions. I need to catch my breath. I need to take water.
It's fine. Thank you. So, any question? We can pause the recording while you get back. I think he left. Any question so far about what we've discussed so far? You can raise your hand if you would like to speak. Okay. Then let me ask you a question if you don't have a question. So what do you understand about inch loss, for example? Anyone? Hello? Abdul Rashid? Chizurum?
Yeah.
My question is that what do you understand
Because the
about
way it works, at least for us, is that
Go ahead, please. Hello?
Can you repeat the question?
So my question was that what do you understand about inch loss? How does it work? And my second question would be, this should be a simpler question. What does regularization do? Anyone want to take that?
I think regularization helps in making your, what they call it, your model to not get used to like a particular data set. I don't know if I'm confusing it with normalization now.
Okay.
Like, so when you introduce like a foreign data after training your model, like when you make use of a new data set, you still get expected results instead of different um, different values from what you're supposed to get, or your model does not misbehave.
Okay, yeah. So it helps
So
you.
is that normalization or regularization?
I mean, you're very close. I think the word you're finding is that it helps you generalize.
Okay.
So,
Okay.
so when you train your model and you get good accuracy, it does not necessarily mean that your model has learned. It might be it's just memorizing. But when you use regularization, it forces your model to generalize. So when you have a new data, you're able to make good prediction. And looking at the graph that Kelechi just pulled up, it's you might look at it might shows you something about having to overfit, underfit, or just good fit.
Okay. So was that Abdul Rashid? I guess it was.
Yes, that was
So
a
y-
question. I
so if
think.
you look at so this from the previous cohort, yeah. So if you look at this plot, yeah, just what you were explaining, this particular plot to the left, extreme left, you find out that the model is trying. This is when you don't use, remember, this is lambda is equal to 0. So you are not using any regularization, right? You find out that your model is trying to learn everything. So now the problem here is that the problem that is defined is that you want to separate, just like in is a classification problem, just like the one of that we are actually treating now. So you find out that the it's unlike the other one where it's just a linear. This one you're trying to is more or less like a non-linear classification problem. Now you see that the line that it's trying to draw, it's trying to perfectly separate the blue points from the, is this green or yellow? From the other point, yeah? The plus from the circle. So it even goes to the extent that even the yellow one that is within the plus region is still trying to draw a circle around it. So it's trying so much to separate all the plus from all the circles, which does not make any sense because this particular one that is inside here might actually even be an outlier, right? So it's for this particular problem, it didn't generalize well. And you see that for the data set itself, that the data set that it is learning from, the error is 91%. So that you have very high training error does not mean that your data, your model is doing very well. It is when you now bring in, yeah?
Immense accuracy.
Oh, sorry, accuracy, don't mind me. Can you imagine? I've said losses throughout today. Okay, so this is your accuracy. It's saying is 91.5%. Yeah. So that's the accuracy. Now it doesn't mean that your model is doing very well. Some people even have 99% accuracy and they feel their model is doing far beyond human, what they call it, human accuracy. Yeah? But that's not actually the case because it only learned from this data and it probably overfitted just like this one here. But if you bring in, trust me, if you bring in external data to this particular model that drew this, it will actually flop. But contrary to this, what you will have is a good, let me just, forgive me to use the word good here, but a moderate model where it kind of generalizes. It's not too specific to separate all the, it does a good job in separating the circles from the plus here. That's the blue from the yellow, but it doesn't go to the extent of trying to find every single detail. And you find out that the lambda value used here is 1, which actually works well. And the training accuracy is 82.2%. So yeah, it doesn't look, it's not up to this 91.5% that we have here, but it's actually going to do a very good job when it sees external data. Contrary, not contrary to that, but another case might be where you pick, because that that the fact that you are the one picking the lambda value doesn't mean you just pick lambda value without understanding the implication of picking wrong lambda values. Yeah. Now, if you pick a very high lambda value, let's say 100 in this case, remember I said lambda. So mathematically, what lambda is trying to do is that it's trying to simplify or reduce the values of your theta. So now, if you use a very high lambda value, it means that it's going to be tending your parameter values towards 0. It means that you are going to be losing a lot of information or a lot of things that your model is going to be able to predict. And you find out that what it plots is just something very small because it doesn't really understand much about the data. You've killed a lot of parameters in that model, right? So when I say parameter, I'm talking of theta, right? So this kind of gives you a visual understanding of what regularization does. Clear? Abdul Rashid, clear? Okay, I guess it's clear. You can just raise your hand if it's clear. Okay, I'm not going through this chart. Okay, it's clear. 14 says it's clear. Okay, so let's go back. Okay, so we were just about to start the logistic regression. So just like we have done in the SVMs, yeah? Remember that we already discussed this. We even went as far as calculating logs and exponents. So this is the logistic loss, right? And it is our loss function. We want to be able to find the gradient out of it. And that leads us into mathematics, right? So after all the mathematics, permit me to do this. After all the mathematics, you can go into more details on your own if you want to, yeah? This is what we come out with as our gradient, right? So it is this gradient. We are just like we did in the other one. We are just going to pick this gradient and plug it into where we are updating the values of theta. So what I mean by that is that we are picking it and we are plugging it into this place here, right? I guess that is clear. And you'll notice that every other thing is the same as what we have had in the previous example, right? And then when you run this, so this kind of gives you the effect of all the behavior of different loss functions. So it should be pointing you to the fact that the way you define your loss function determines how well you optimize your problem, right? And again, here we are not using the first normalization method that we used before. We're using the last one, right? That I told you I prefer using. And then this is what we have as our values of theta. So I've not actually compared it, but let's compare these values of theta to what we have in the previous example. Let's see what it looks like. Yeah, I think it's somewhere. Yeah, so it's kind of different, right? It's kind of different. So what I would say is, yeah, you're using a different loss function. So you would probably not have the same values of theta, but they'll both do the same. They'll actually still do the same job, right? Okay. And then we can plot. We can plot to see. So you see, it still does the same job. It does a good job, right? And look at this particular one. Look at this particular one. Notice these 2 points: the plus, the red plus here, and this blue X here for these values of theta. Yeah? And compare it to the one we plotted here. Here. So you see this plus and this X. So you see that it's kind of very, 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 very close, right? So maybe I should actually see the values of theta here. Okay, just give me 1 sec. I hope this doesn't mess up things. Why am I still? Okay, so you see, now this one is even totally different from what we have here. Yeah. So it's kind of different from what we have here. So the fact that you're not having the same, you shouldn't actually be aiming to having the same values of theta for the different, for when you're using different loss functions. But most important thing is that you're reducing your loss and then you're getting the same result, right? Okay. So I don't mess things up, I'll probably have to, I'll have to just run this again. Okay, and then we can plot the loss. And you'd see that the loss kind of reduces, yeah? This one is similar to the one we have for linear regression, and then the one for, so Teslim wants to ask a question. This is the loss. So Teslim.
Wake up.
Okay.
You never wake up.
Hello. Okay. Maybe he's not ready. Okay. So, okay, how do we go about selecting the lambda aside manual testing suggested by your explanation, in your explanation? I don't know of any way, or maybe any automatic way of selecting your lambda value, but I don't know, Teju, do you know of any automatic way of, or mathematical way of selecting your lambda value? But what I know is that you try out, there's a range of values, there's an intuitive range of values of lambda that you would normally pick, range of lambda that you would normally pick from, right? I don't know, except if there's a new research and then somebody has figured out something. Of course, research happens.
It's an hyperparameter search. You have to search and decide on what works for you, because your data, we have different data sets and usually they beg different technique. So if you're using things like AutoML, it does the hyperparameter search for you to find the most optimal. Another way people use to find hyperparameters like that is to read a lot of research paper, because a lot of researchers have tried different things. So you can cancel out the things. It can inform your intuition about what things to try out and what things not to try out, so you don't waste your time. Or as someone who's just starting out the field, just try out a bunch of things to see how does it behave. You have to be able to understand that yourself as well.
Okay, thanks. Okay, so we are almost rounding up, right? Might be a bit faster now because of power. Okay, so next is multi-classification. What we've been doing so far, right? It's basically binary classification. That's the truth. So it's binary classification we have actually been working with. But you can have cases where it's more than one class, right? So let's say you have, now this is cancer prediction, so it's malignant benign. Let's say you have, thinking of an example. The only thing that is coming to my head is computer vision. That's images. Let me just use it that way. So let's say you want to differentiate between a cat, a dog, and a goat, or a cat, a dog, a goat, and a cow. So this
Or you
is
want to differentiate between different breeds of cats.
exactly, or you want to differentiate between different breeds of cats, right? So now, for different breeds of cats, you can have close to, let's say your data set, you might even have up to 15 cats, right? Now the question is, how do you differentiate? How do you build a classifier that is not as simple as the binary ones you have been seeing? That is not as simple as the ones that solve for binary problems like you have been seeing. So there's a method called, he didn't really go into multi-class classification here, but for multi-classification, there are a lot of methods that exist out there. But here he was talking about the one versus all method. So basically what it does is that it kind of creates a classifier for the different classes. Forgive me to use that word, right? So it's like saying for your cat, you want to create a classifier to predict whether it's a cat or a dog, a cat or not a cat. For your dog, you want to predict if it is a dog or not a dog. So most times you have, if you're trying to visualize it, you would have maybe different linear plots on your graph, right? Trying to distinguish, is this, is this not this, is this? And then advances go further here to where you use softmax and then reduce it to probability, right? So that's what you would normally have in computer vision, where your output will be a probability over all the classes, and then you pick the one that has the maximum probability, right? So, but he didn't go into multi-class classification here. I think he went into multi-class classification later. But even if he doesn't touch multi-class classification, I'll try as much as possible to chip it in. So for linear regression, I know he touched it a bit, but I'm most likely going to give either a practice work or an assignment on something that is around multi-class classification, multi-class regression problem. Yeah. Okay. So that's just the nutshell of multi-class classification. So then, of course, everybody knows scikit-learn. Everybody should know scikit-learn by now, right? So now everything we've done in using our codes, you can actually achieve them with scikit-learn. Sweet thing is that even the aspect of introducing one's vector into your features, you don't need to do that with scikit-learn. Scikit-learn does that for you. And then for all of us who have actually judiciously explored scikit-learn, you would understand most of the terminologies in scikit-learn. So here, using the standard scalar and fits and transform, it's just a method of normalizing your data. So if you read here, you'd see it computes the mean and variance of, okay, so that's dot fit, right? Computes the mean and variance of a column, right? And dot transform converts the data to have 0 mean and unit variance. So that is how, if that is what you want to use as for your normalization, when you want to use scikit-learn, you don't actually need to explicitly write the equations. Scikit-learn has these equations in them, and you can just pass in your data into these functions and get your output, right? And for SVMs, scikit-learn has an SVM function. They call it SVC. No, so it's an SVM package. So inside the SVM package, you have the SVC. And SVC, you can then define whether it is a linear kernel or a non-linear one, right? And then you define C. So C is the inverse of your normalization. So scikit-learn doesn't use, they don't take in the regularization parameter as you would have passed it in your equation above. What you would instead have, I think it's written somewhere down here. What you would instead have is the inverse. So it's like the inverse of what you have here, right? That is what you would have as your C. So this is what you would write in your own equation, and this is what scikit-learn will use, right? I'm not sure you're going to have any difference in any of these two, right? Even if there's difference, it's very subtle, yeah. And then another thing, scikit-learn doesn't apply regularization to the constant feature term, that's theta, right? Theta 3. So in our own case, we actually apply regularizations to theta 3, right? So theta 3 is like your intercept, like we have said before. So we would normally apply our own regularization method. Our own method of regularization will also apply regularization to the theta 3. But for yeah.
No, I was just gonna say that yeah, C can be thought of as regularization technique, but usually it's called merging, and it's just a lot of mathematical details. So that's why it's easier to just say it has been mathematically proven that it's the inverse of regularization. But if you want to, in case you're looking for the mathematical term itself, and you want to learn more about SVMs and all, so it's the merging. It helps you kind of like, if I can just go a little bit into SVM. So usually when you're trying to, SVM can be very strict. It means that you either belong to one class or you belong to another. It does not give you, there's no, if you're not within, you need to have a margin. So if you're not far from it, then you're unable to use SVM to do your classification. So that's like the hard margin case. So the C itself helps you do something called soft merging, whereby you allow your model, some of your examples to be wrong, to like they can fall into the wrong category. So the hard margin does not so if you're what's that word where you're an outlier? Yeah. So for hard margin case, if you're an outlier, it's like it still want to be able to maximize and want to be able to find a margin in such a way that it separates both classes. That's the goal of the SVM. It just wants to separate the classes as much as it can. But soft margin helps you account for the fact that there could be outliers. So the C parameter itself accounts for that. That's why it's important.
Okay. Clear? I guess it's clear. Don't worry, guys. Yes, mathematics. By the time you start practicing, the mathematics if the mathematics is turning your head, just remove it. Just practice something. You get? I'll look for data and send to you guys. Forget all the whole explanation and then just pick the algorithm and try to train and then see how it improves and then try out predictions. So I'll look for data sets that I can send to you.
We cannot stress that point enough. It's understandable that the math might be a little bit confusing at the moment, and it's very, very important and good that you understand how it works, but you should not let that limit you. Start by trying to get familiar with the tools itself. Try to use a lot of data, like just experiment. From experimenting, you would have questions, and from having questions, the theory will support you. You get, so like if you go from the theory at first, it might be a little bit daunting if you don't have other goals, you know, which is maybe if you have to study it or something. Those are like go on their own. But if you're just like studying just to understand something, it might look like, okay, when are we ever going to use this? So you can start from, I would encourage that we start from trying to fit. You can even start from scikit-learn itself, like just get data in, look at what's happening, try to understand what's happening. Then once you start having all these questions and you want to have more power in terms of how these things are working, then you start digging into the math and trying to understand what it works. But always go with the goal. Okay, I have a problem. Formulating the problem itself is a big deal. So don't let the math be a barrier. Start by formulating, like looking at different problems and seeing how can you use machine learning tools to solve them. That should be your immediate goal, not the mathematics itself.
Okay, thanks. So I think it's 12:30. Time has gone. But nice. We're actually at the end. So let me just quickly go through. So there's there's another function, linear SVC, which is a bit different from the one we used here. I can't remember where it is, but the one we used before, right? So linear SVC also does the same thing. It plots linear, tries to fit a model, right? That is linear. And here you can define the loss. So we defined a hinge loss, right? And then we already know what C does, right? And then you can fit and plot, right? To see what it looks like. Okay, sorry. I wasn't running this. Let me quickly run it. Right. Okay. Okay, this is okay, so yeah. So you see that this one actually still works fine too. And then you also have your logistic regression in scikit-learn. So you can just throw in your data to scikit-learn and then select the logistic, load up the logistic regression model and then plot. So you see it actually works well too. So scikit-learn is quite optimized, yeah? And I think everyone should also try it out, in as much as you're trying the codes, yeah? I think that's it for today. Unfortunately, Teslim has a question. Can we take the question on Slack?
Oh, that was.
Oh, okay, okay.
That was
Okay. Okay, so I think we can call it a day. It's past 12:30. The deep learning guys have to start now. So thanks so much. Please, guys, try as much as possible to go through everything we did last week and this week and ask questions on Slack. I'm there. I'm happy. I was really happy when Fortune put up his stuff, although I've not had, I'll still go back to it to see what he did. But nice one, Fortune. If you're doing stuff, please put it on the group and encourage others to do the same. And if you know the question, if you know the answer to a question anyone puts up on Slack, please answer it. You are doing yourself good by getting better. Even if you have an idea you're not sure, try it on your own to kind of figure out the answer. That way you're actually improving yourself, yeah? So thank you very much, guys. Have a lovely weekend. I'll be on Slack waiting for you guys. Thank you.